In addition to direct impacts from individual agentic AI systems, there will be indirect impacts that result collectively from the usage of many different AI systems and society's reaction to their usage. Just as it would have been difficult to anticipate the full range of societal readjustments from previous general-purpose technologies like electricity and computers, one should expect the unexpected. Still, we do think there are several categories of indirect impacts from agentic AI systems that are likely to require active mitigation by society, which we list below. These indirect impacts may be addressed at least in part by adopting best practices for users, system deployers, and model developers, such as those outlined in Section 4. However, fully addressing these complex challenges will likely require additional strategies beyond this paper's proposals, including through industry-wide collaborations and society-wide mitigations. Some strategies towards this end may be domain or risk-specific, while others may involve placing general requirements on the usage of certain types of agentic AI systems. 5.1 Adoption Races. Given the advantages that agents may confer in competitive environments, such as competition between private firms or governments, there may be significant pressure for competitors to adopt agentic AI systems without properly vetting those systems' reliability and trustworthiness. A key observation driving such premature reliance is that agentic AI systems may succeed at a task on average while being unreliable in rare but important cases, which can be missed or ignored by competitors under pressure. For example, consider a hypothetical class of agentic AI code generation systems that can rapidly write new code, but whose code occasionally contains serious security flaws. If a software development company thinks their competitor has been using these coding systems without human supervision as a way to quickly build new features, they may feel pressured to do the same without doing proper due diligence, as they might otherwise lose market share to their competitor. As a result, all firms' codebases would now be vulnerable to serious cyber attacks, even if each individual firm would have preferred to go slower and thereby avoid this outcome. This trend toward over-rapid adoption, even in high-risk domains, can lead to over-reliance, whereby humans trust agentic AI systems without fully understanding their limitations. This could create the conditions for widespread use of unsafe AI systems that, in the worst case, may prove catastrophic. 5.2 Labor displacement and differential adoption rates. Agentic AI systems appear likely to have a more substantive impact on workers, jobs, and productivity than static AI systems. Traditional AI systems excel at some routine work, but increasing agenticness could expand what tasks are routine enough to be assisted or automated by AI, such as by adapting to unexpected conditions, gathering relevant context, and calibrating to a user's preferences. This means they may expose a greater number of jobs and tasks to augmentation and automation, similar to other axes of AI system improvement like tool use. This could result in a range of different economic effects. These could lead to substantive boosts in worker productivity and economic growth, but could also result in the displacement of a large number of workers, either because their jobs are fully automated or because their skills are made less rare, and thus their jobs become more precarious. At the same time, agentic AI systems may improve education and enable workers to upskill into new jobs. It is also possible that agentic AI systems can increase the agency and productivity of individual workers or small firms more than traditional AI systems have done, such as by increasing the availability of previously rare expertise. This may or may not offset large firms' advantages in capital, e.g. their ability to run more agents, and pre-existing market position, such as firms with access to proprietary data that can be used to train bespoke agents. Even similarly positioned individuals and firms may differ in their ability to leverage agentic AI systems. Different individuals' jobs and firms' business strategies may be more or less amenable to AI agent automation, depending on the particular order in which each AI agent capability is unlocked and becomes reliable. Individuals who lack digital literacy, technology access, or representation in design decisions around agentic AI systems may find themselves less able to participate in an agentic AI system-fueled world. However, AI agents could also reduce the technology access gap, much like smartphones increased internet access to underserved populations, though some gaps remain. All these effects may alter the job landscape and business environment unevenly and increase the importance of taking active policy measures to ensure the benefits of increasingly agentic AI systems are in fact shared broadly. 5.3. Shifting offense-defense balances. Some tasks may be more susceptible to automation by agentic AI systems than others. This asymmetry is likely to undermine many current implicit assumptions that undergird harm mitigation equilibria in our society, known as offense-defense balances, with unclear consequences. For example, in the cyber domain, human monitoring and incident response is still key to cyber attack mitigation. The feasibility of such human monitoring is predicated on the fact that the volume of attacks is similarly constrained by the number of human attackers. Consider the hypothetical where agentic AI systems can substantially automate cyber attacker responsibilities and thus dramatically expand the volume of attacks. But cyber defender responsibilities, such as monitoring, are much harder to automate. In such a world, the overall effect of agentic AI systems would be to make cyber defense less viable and make information systems less secure. Conversely, if agentic AI systems make monitoring and response cheaper than producing new cyber attacks, the overall effect would be to make cyber defense cheaper and easier. While it is very difficult to anticipate the net effect of agent adoption dynamics in a particular domain in advance, one can be confident that some processes will be much more amenable to automation than others, and that numerous societal equilibria may shift as a result. It behooves actors to pay close attention in identifying which equilibrium assumptions no longer hold, and to quickly respond, such as by investing in differential technological development towards defender-oriented technologies. 5.4. Correlated failures. Agentic AI systems may bring unexpected failure modes, and a particular risk arises when a large number of AI systems all fail at the same time, or all fail in the same way. These correlated errors can occur due to algorithmic monoculture, the observation that AI systems trained using the same or similar algorithms and data can make them malfunction in similar ways. There is already evidence that language models trained on similar data distributions suffer from similar vulnerabilities, such as adversarial prompts that corrupt one system generalizing to corrupting other similarly trained systems. Similarly, biases in common training datasets, when used by many different model developers, could expand the biased behavior of individual AI systems into a society-wide harm, such as by all agents suppressing the same news article in recommendations or reinforcing stereotyped representations against the same social group. More broadly, AI systems may be vulnerable to disruption in shared infrastructure, e.g. power or internet outages. Such correlated failures may be more dangerous in agentic AI systems as they could be delegated more power by humans, and thus the potential consequences of their failure could be greater. They may also be exacerbated because agentic AI systems may shape each other's information environments and even directly communicate with each other, allowing for much more direct and even deliberate propagation of certain failures. It is particularly challenging to guard against such correlated failures because they are a joint function of the individual AI system and its constantly changing environment. One initial path forward is to create visibility and monitoring in the agentic AI ecosystem to catch such wide-scale issues as they emerge. Correlated failures may be particularly hard to deal with because they may overtax the fallback systems intended to remedy individual agents' failures, but which are unprepared for large-scale failures. This may be especially acute in cases where the fallback plan is to have humans manually take over for each malfunctioning agent. For example, if a company's loan approval chatbot generally fails 1% of the time and has a small number of staffers to handle those failures, then a rare correlated failure that takes down 100% of the chatbots would bring the loan approval system to a halt. However, the rarity of this risk may make it difficult to discern from routine operation alone, and thus could make it challenging for concerned employees inside the company to justify the cost of retaining adequate staff for such a seemingly hypothetical failure. In the longer term, if as certain human tasks are entirely replaced by agentic AI systems, human expertise in certain domains may atrophy and make us entirely dependent on agentic AI systems and their attendant failure modes. It may be particularly important for policymakers and the AI ecosystem to find ways to ensure that fallback mechanisms for agentic AI systems are robust to these sorts of correlated failures.